In this video, I'm going to solve a few problems that are limit problems involving infinity. The idea being that perhaps if you watch this video, it'll guide you, give you some hints, some techniques to help you move forward with your homework if your homework involves infinity and you want to take a limit. All right? So I'm just going to pick several examples here. We'll start with something like this one. Say something like, out of my book, number 15, we want the limit as x approaches 1 of 2 minus x divided by x minus 1 quantity squared. Now, when we work with limits involving infinity, we have to realize that an answer, just like when we were doing limits with the limit laws, an answer of 0 divided by 0 is not what we're looking for. What we're looking for are choices, right? Are possible solutions. Right? Are possible solutions to problems like this. We might get an answer of plus infinity. We might get an answer of negative infinity. We might get an answer of fails to exist. These are our possible solutions. Okay? And we have to determine which of those solutions, and we might get a real number. We have to determine which of these solutions is going to apply to our problem. Just saying fails to exist every time we do a problem involving infinity, that's not going to lead us to the correct answer. Right? That's not going to get us the maximum number of points on an exam or a quiz. In fact, it's usually going to get us the minimum number of points on said exam or quiz. So here we sit, we have this problem, we try to plug it in, right? We're not going to change our technique. Our technique is still going to be, I just want to plug it in. And if I can't plug it in, I'm going to try some algebraic manipulation. If that doesn't work, I'm not going to the squeeze theorem on any of these problems. But this is how we're going to try to solve the problems. So when we plug in 1 in the numerator, we get a 1. Right? 2 minus 1 is 1. Feels like we're on our way. When we plug 1 in the denominator, though, we get 0. Well, it's 0 squared, but 0 squared is still 0. And this is not good. Right? It's not good. It's not bad. It's just the wrong answer. So it tells me that I'm not going to get a real number here necessarily, but I've got to try. I've got to go through my steps. So my next step after I try to just plug it in is I'm going to take the limit as x approaches 1. I'm going to rewrite this as 2 minus x, of course. My denominator clearly, is x minus 1 times x minus 1, x minus 1 squared. Now the problem is I have 0 times 0 here. And so this is what happens when we do limits involving infinity. We can't stop here. This isn't where we stop. This is just the beginning. So what am I going to do? I'm going to have to consider two cases. I'm going to have to take a look at case 1. And I'm going to have to take the limit of this as x approaches 1 from below of 2 minus x over x minus 1 times x minus 1. All right, this is what I'm going to have to do. So what is this going to give me? Well, I don't know. I'm going to have to do some analysis. Okay, so unlike limits involving the limit laws, where ultimately we do our algebraic manipulation, we plug things in, we get a number to come out, we look in the back of the book, the number matches our number, we feel good about ourselves. We look in the back of the book, the number doesn't match our number. We then figure out what algebraic mistake we might have made, and we fix it, and we again get the correct answer. Here we're going to have to do some analysis. We're going to have to ask ourselves, what does this look like? In pre-calc, we learned if you have a linear term in the denominator, such as we do here, x minus 1, then 1 is not going to be in the domain. We also learned that one of two things happens. If this x minus 1 cancels with an x minus 1 on the numerator, and it's the only factor that is x minus 1, our graph would have a hole. However, if this x minus 1 does not cancel with an x minus 1 in the numerator, we said our graph had a vertical asymptote. Well, clearly our x minus 1 in the denominator doesn't cancel with the x minus 1 in the numerator because we don't have an x minus 1 in the numerator. So we have a vertical asymptote. Now what does that mean? Well, it means we have a vertical asymptote at 1. If we were to look at the graph of this function, at 1, we have a vertical asymptote. Now we're approaching 1 from below. We're trying to determine, as my graph approaches this asymptote, is it going up to positive infinity, or is it going down to negative infinity? And the way we're going to do this is we're going to pick a number close to 1, smaller than 1, a number on the left-hand side of 1, and we're going to plug it in, and we're going to ask ourselves, what's happening? We're going to see it grows without bound, but we're going to have to ask ourselves, is it growing without bound in a positive manner or growing without bound in a negative manner, right? This is plus up here, and this is minus down here. The analysis isn't going to be overly complex. It's not going to be overcomplicated. We're going to pick a number really close to 1, but below 1. You know, 0.99999 with as many 9s as you and I can imagine. And we're going to take that number and we're going to plug it in. So if we take a number close to 1, but a little bit smaller than 1, right? Here's 1. We're on this side of 1. We have a number smaller than 1, but barely smaller than 1. When we plug it into 2 minus x, we have 2 minus a number that's essentially 1. That's going to give us a positive result. 2 minus a number that is essentially 1 is going to give us a positive result. When I plug it in the denominator, now remember my number is smaller than 1. It is to the left of 1 because we're approaching from below. It is to the left of 1. When I plug a number in below 1 and I take that number minus 1, I get a negative value back. Now I don't care what the number is. We're not going to use our calculator to evaluate this. All I need to know is I get a negative number. And it's not very big. In fact, it's tiny, right? I like to tell my calculus students that what we get here is negative tiny. Now that is not advanced mathematics. That's not mathematics at all. If anybody that, watches this video knew me in graduate school, or Lord forbid any of my graduate professors watch this video, they're not going to be overly impressed with this. But for you and for me doing what we're doing right now, this works for us. We have a very tiny number. Why? Because I'm taking, remember what we have here, we're letting A equal 0.9999. And it goes for a while. When I subtract 1 then, I don't get a very big number, but it is negative. Here, I also, because this is equivalent to this, I also get a negative tiny number. Now on the top, we have what's in essence 1, right? That's what we said. It's not really 1. We could even, since we're already, kind of throwing math out the window here, we could say it's 1-ish, right? It's a little bit bigger than 1, but it's 1-ish. Now what's going on? If I take a negative tiny number times a negative tiny number, multiply those together, I get a positive tiny number. So what I'm looking at here is 1-ish on the top, which is positive, and I have a positive tiny number on the bottom. I told you we were going to do analysis here. We're not going to do calculations. We're going to think, right? We're going to do this in our heads while writing it down this way. But we're never going to do this calculation. We're not going to pull out a calculator and ask ourselves, what does this equal? So I'm going to take 1, and I'm going to divide it by a positive tiny number. I have a positive divided by a positive. That's going to give me a positive result. When I take 1 and divide it by an infinitely small number, an infinitely small number goes into 1 an infinitely large number of times, and therein lies our result. From below, we're going to positive infinity. This is how we do limits involving infinity when we have things like 1 divided by 0 and we have to evaluate it. Well, that was case 1. Now we have to do case 2. Right? And we know what case 2 is going to be. It's going to be the limit as x approaches 1 from above of 2 minus x divided by x minus 1 times x minus 1. The contrast here, of course, is we're approaching 1 from above. We're coming from this side. So no longer is a going to be 0.99999. Now we're going to let a equal 1.000000, And out here someplace, right, we throw in a 17 or something. We have a tiny number, sorry. We have a number that's a tiny bit bigger than 1. Now, when I take that number and subtract it from 2, that number's a little bit bigger than 1. We're going to have to borrow and do all those interesting things. But in essence, it's going to be positive, and it's going to be really close to 1. What's going to happen in the denominator? Well, I have this number minus 1. I'm going to have this is my result. This is going to be a positive number that is tiny. Here, I'm going to have another factor that's a positive number that's tiny. And what do I end up with? I end up with a positive number on the top that's positive 1-ish. And on the bottom, I have a positive tiny number. We've already done that analysis. That gets us plus infinity. Now this matches this. The limit from below matches the limit from above. And because the limit from below matches the limit from above, and they asked us about the two-sided limit, we're now going to provide them with an answer. The limit as x approaches 1 of 2 minus x divided by x minus 1 squared is going to equal positive infinity. Positive infinity. Positive infinity because they match. If the limit from below had been positive infinity, but the limit from above had been negative infinity, then I would be able to tell you what the one-sided limits were, right? This one would be plus, this one would be minus, for example. But here I would say fails to exist because they do not agree. Okay? So this is how we're going to work out limits involving infinity. They're a lot more fun than the limits involving the limit laws because we get to play with our imagination, and that's always more enjoyable. All right, so let's take a look at another limit problem involving infinity. See if we can throw in a different technique. Another possible problem might be a problem that works out like this. 22 from my book. The limit, but this time x is approaching infinity. And we have a rational function, 3x plus 5 divided by x minus 4. Okay, this is a very common limit problem where you're working with limits involving infinity. So what are we going to do when we address this problem? Well, obviously we can't plug infinity in here. We get 3 times infinity. We don't know what 3 times infinity is. You can't write 3 times infinity. Infinity is not a number. All right, so infinity, the algebra we know does not apply to infinity because the algebra we know applies to the reals, and we don't have the reals here, so we have infinity, so we can't do that. We can't plug it in. So the steps we've seen in the past, that just plug it in steps, they're not going to apply here. So if we're going to infinity, we're not going to plug in steps. We know what this means from pre-calc. From pre-calc, we know this is really asking us, does this function have a horizontal asymptote as x grows without bound, right? That's what we've been taught. We were taught, maybe not in pre-calc did we talk about it in the context of x approaching infinity, but out in our book, in this section, our author clearly indicated to us that if your limit is going to infinity or negative infinity, that is a horizontal asymptote question. We're not going to graph this like we did in pre-calc and address this from a horizontal asymptote perspective. We're going to move forward and try to find an algebraic technique that will allow us to solve this. And here's what we do. We divide each term by the highest power of x, or the largest power of x in our denominator. Now that's really important. The technique says in the denominator, you take the highest power of x found in your denominator. If I look in my denominator, the highest power of x is x to the first, so I'm going to rewrite this as the limit as x approaches infinity of 3x divided by x to the first plus 5 divided by x to the first divided by x divided by x to the first minus 4 divided by x to the first. Again, highest power of x in the denominator. I'm going to simplify each of these. I'm allowed to simplify each of these. X is going to infinity. Remember, 0 divided by 0 is the only ratio of two real numbers that does not equal 1. Right? It's the only ratio of two identical, real numbers that does not equal 1. And we know x is not 0 because 0 doesn't live anywhere near infinity. So when we simplify this, this becomes the limit as x approaches infinity. This just becomes 3. This is 5 over x. This is 1, and this is 4 over x. All right? Now, where are we going to go from here? We're going to plug in infinity. We're going to ask ourselves, what happens when I take this limit? This is a constant, so the limit of a constant is the constant. When I plug this in, this is plus. Now, I'm going to write something here that's not mathematically valid, but it is what I'm going to write. And down here, I'm going to have a constant, and I have 4 divided by infinity. Now, what does that give me? Well, 5 divided by an infinitely large number, right? That approaches 0. 4 divided by an infinitely large number approaches 0, and we find out that 3 divided by 1 is our answer, so our solution is 3. This technique of dividing each term by the largest power of x in our denominator, of course, if your variable is not x, this is not going to be an x. But this technique is going to work for us. So let's take a look at another problem, because there's a bit of a hiccup here. Say we have the limit as x goes to infinity. And we have, instead of this, we have x plus 2 divided by the square root of 9x squared plus 1. Right? So this is what we have. When we look at this problem, we're focusing on the denominator. We're focusing on the denominator. So when we focus on the denominator, we see an x squared. Now it's under a radical, and that's going to pose a bit of an analysis step for us. We're going to have to think through what to do here. Well, again, we know x is not 0, so we're going to feel free to divide. The largest power of x in the denominator is x squared, as long as we're under the radical, right? As long as we're under the radical. So we're going to rewrite this as the limit as x approaches infinity. We're going to rewrite this. Our denominator, remember, we have a radical, so we have 9x squared divided by x squared plus 1 divided by x squared. Right? Nothing happens down there. We just divide by the highest power of x. Now, this is x squared under a radical. We know from algebra 2 the square root of x squared equals the absolute value of x. And we know the absolute value of x is either x or the opposite of x. It's x if x is greater than or equal to 0. It's the opposite of x if x is less than 0. Now we have to keep that in mind. In our case, we're positive. X is greater than 0. We're going to positive infinity, which means when I take the square root of x squared, because I divided by x squared under the radical, this doesn't have a radical, so when I rewrite my numerator, I have to write x here because our x is positive and the absolute value of x gets replaced by x. If this was going to negative infinity, that would be a minus x. And that's very significant because it's going to change your answer. There's an example of that in every calculus book. Make sure you read that example if what I told you right there was not clear. Now I have plus 2. Again, I get to divide by positive x. When I simplify this, what do I get? I get the limit as x approaches infinity. I get 1 plus 2 over x divided by the square root of 9 here plus 1 over x squared. And now we're ready to let x grow without bound. When x grows without bound here, we get 0. When x grows without bound in this term, we get 0. These are constants. I get 1 divided by the square root of 9, or I get 1/3. Okay. So this is another technique that you are going to have to master. And it involves this analysis of the square root of x squared. Now, if this is the cube root, we don't care. Right? It's only even roots that come out like this. If I have the 4th root of x to the 4th, 6th root of x to the 6th, I have to worry about the absolute value. All right?